In this video, we are going to see about the deformation due to the external force acting on the body and deformation due to the self-weight of the body. To know about the deformation, we should know about stress, strain and Young's modulus and the mass density and weight density of the material. What is stress? Both stress and strength are irrelatable. Strength is the measure of the amount of the stress a material can withstand without breaking. It is the ability of the material to absorb the maximum load before it breaks. So consider a elastic material. So when you stretch, what happens? It elongates in the linear direction and also in the lateral direction. So the length is elongated and the diameter is reduced. So at one particular time, the neck is forming where the maximum stress is applied. So once the neck is formed, the object is about to fail. So finally, the fracture will happen. So the stress is the internal resistance offered by the body against externally applied forces. So stress is force per unit area. The unit is Newton per meter square. Strain is the deformation of material from the stress. It is the ratio of change in dimension to the original dimension. Suppose if you take longitudinal side, you can tell change in length by original length. If I take lateral side, you can tell change in diameter by original diameter. Strain has no unit. The Hooke's law states that within the elastic limit, the extension is proportional to the force. So the Young's modulus is the ratio of stress to the strain. The unit of Young's modulus is Newton per meter square. So the Young's modulus is the measure of the stiffness of the material. When the Young's modulus is very low, the material is very flexible. When the Young's modulus is very high, the material is rigid. So this is the bubble graph which shows the variation of density with respect to the Young's modulus. When the density is low, we can tell the material is lightweight. When the density is very high, we can tell the material is heavy. Similarly, when the Young's modulus is very low, we can tell it is a flexible material, and Young's modulus is very high, we can tell it is a stiffer material. The foams and wooden products are light, but it has very less Young's modulus. Similarly, the metals and alloys and ceramics are heavy and they are stiff also. So coming to the stress and strain graph between the three different types of materials, brittle material, ductile material and plastic material, we can tell the Young's modulus as the slope of the stress strain curve. When the slope is very high, we can tell the brittle material, the slope is very high, so the Young's modulus is very high. The ductile material, the slope is average. It lies in the range of plastic material to the brittle material. So the ductile material has the medium Young's modulus and the plastic material has the very low Young's modulus. Mass density or density. So the density is the property of the which describes the compactness of the substance. If the substance is very compact, we can tell it is a high density. It is less compact, we can tell it is a low density. So mathematically, we can tell the density is the mass per unit volume. The SI unit is kg per meter cube. So here in the water, the wood floats on the water. Similarly, cork floats on the water and the ice cube floats on the water. But the stone and the iron nail sinks in the water. It shows that whenever the object is the lesser density floats with the higher density sinks. Specific weight or weight density. The specific weight is defined as the weight per unit volume. So the unit is Newton per meter cube. So deformation. So what is this deformation? When you apply the force axially, either it may be a compressive force or it may be a tensile force. What happens? The body will elongate or contract. This elongation and contraction is said to be deformation. So this deformation will depends upon load acting on the body and the length of the body, similarly the cross-sectional area of the body and also the stiffness of the material. Similarly, when considering the deformation of the body due to the self weight, when the body is hanging freely or suspended freely, the weight of the body will be acting as the load and the length of the body plays into the account. Similarly, the area and stiffness also comes into the play. So coming to the deformation due to the external forces, so let P be the tensile force acting on the body. It is the axial force. So del L. So once the tensile force, what happens? The deformation in the length will be happens. It is positive. In the lateral dimension, deformation in the negative will happen. So that is the diameter will be reduced. Similarly, take in the opposite case, when it is a compressive force, what happens? The length will be reduced. We can tell it is a negative deformation and the diameter is increased. We can tell in the lateral side it has the positive deformation. So considering the tensile force P, to arrive the relation of deformation of the body due to the external force, so initially before the application of the force, we can tell the length of the bar is L, it is taken as in mm, and diameter of the bar is taken. Similarly, E, the Young's modulus of the material is taken, that is the stiffness of the material, and the tensile force acting on the body is taken. After the application of force, the stress is induced in the body. Due to the stress, strain is created and the deformation is going to happen. So stress is the unit, have Newton per millimeter square, and strain, since it is a ratio, have the no unit. The change in length is positive side, since it is a case of a tensile force. Similarly, the diameter is in the lateral side dimension, it reduces, so you can take it as a negative. So unit is mm. So you know the equations. Stress represented by sigma is force per unit area. Strain, the change in dimension to the original dimension. Young's modulus, stress by strain. So you know the equation of stress. Stress is load by area and strain is change in length by original length. So now substituting in the equation of the Young's modulus, you can get P by A divided by del L by L. So you will be finally getting the equation E is equal to PL by A into del L. So taking del L, you can get the del L equation as PL by AE, where del L is the deformation in the axial length. So coming to the deformation, right, this equation del L is equal to PL by AE. This equation is also applicable to the compressive force also. Mostly this case we have taken the example of the tensile load. We can apply the same thing in the compressive loads also, when the tensile stress is taken as positive, whereas compressive stress and strain is taken as a negative. Coming to the deformation of the body due to the self weight, or when the body is hanging freely, take this figure, a bar of length AB, or sorry, bar of length AL is hanging freely. So the length of the bar is taken into account, the cross-sectional area is taken into account, the Young's modulus E, that is stiffness of the material. The weight of the material comes into play here. Since it is suspended freely, the object gets deformed due to its own weight. So weight here is equal to small w into AL. That is nothing but small w is nothing but specific weight. A is nothing but the cross-sectional area of the material, and L is nothing but the length of the bar. So coming to the derivation, we can take a small section dx of the bar at a distance of b from the bottom end. So the weight of the bar for the length of x, the x is the length of, at the length of x, dx is situated. So what happens? The load P is equal to specific weight into area into the distance. So the elongation of the small section of the bar due to the weight of the bar, we can tell it as PL by AE. From the previous relation, we can tell del L is equal to PL by AE. Now I'm substituting the value of P. What is the value of P? P is equal to W, specific weight, into area into X, the length of the position, into the small element dx divided by AE. So I'll getting the final equation will be getting as Wx into dx by E. So the total elongation of the bar we can found out by integrating the above equation with respect to the 0 to the L. So integrating with respect to 0 to L, of Wx into dx by E, we will be getting W by E taken as constant. Then we can take it as 0 to L x into dx. On integrating, we will be getting W by E. So on integrating x dx, we will be getting x squared by 2, the lower limit of 0 to upper limit of 1. So finally, you will be solving, you will be getting W into small l square by 2e. So here you will be substituting the value of W. The value of W is capital W by AL into L squared by 2e. So on reducing it, you will be getting del L is equal to WL by 2AE. So the deformation of the bar due to the own weight is equal to half of the deformation if the same body is subjected to the direct load equal to the weight of the body. So the equations to the remember, stress, stress is the ratio of force to area, strain is the ratio of change in dimension to the original dimension, Young's modulus is the ratio of stress to strain, and from the above equation we can derive strain is equal to stress divided by Young's modulus. And there are two main equations to remember: deformation of the body due to the external force, that is del L is equal to PL by AE. Similarly, due to its self weight, del L is equal to WL divided by 2AE. So in this video, we have seen what is deformation and what is stress and strain and what is Young's modulus, how the Young's modulus, the value of Young's modulus is related with stiffness, and what is mass density and weight density, and finally the two derivations, deformation of the body due to the external forces acting on the body and the deformation of the body due to its self weight. Thank you.